Hey guys, so this is the second and final video of the gas law notes. And so what we're going to talk about is the ideal gas law. And what the ideal gas law does is it combines moles, pressure, volume, and temperature. So the amount of the substance, how much force is being put on it, the amount of space it takes up, and how much kinetic energy is causing these atoms to move around. And the reason why it's called ideal is because a lot of times gases don't behave the way we want them to, and so but when they behave under ideal conditions, certain assumptions are made and things like that, and we could go into it, but we're not going to. We just want to talk about the math with it. And so the formula for the ideal gas law is PV equals nRT. Right now, we know that P stands for pressure, and remember, most of the time we measure pressure in atmospheres. That does not mean at the moment, but atmospheres, although there are like 5 other units, so be prepared. Volume is, or V is volume, and it's measured in liters. N is equal to your moles, okay, and that's going to be a little bit different. T is temperature, and we know that because these are gases, it should be in Kelvin. And then R. Okay, R is the ideal gas law constant. Okay, now this ideal gas law constant has several values, but those values are different based on what unit they use to measure pressure with. So one of the gas laws, so R can equal, the first one that you'll see on the back of your periodic table is 0.0821, okay, and it's going to have 4 different units in it. Liters times atmospheres divided by moles times Kelvin. Okay, all of that is for that one number. Okay, but R can also be equal to 8.314, and this is for when liters times kilopascals divided by moles times Kelvin, but it can also be equal to 62.4 liters times torr divided by moles times Kelvin. Okay, and so the difference between these are what unit they measure pressure with. So here in 0.821 it's atmospheres, here it's kilopascals, and here it's torr. So you need to pay attention to what unit of pressure you have, and that will determine what unit you will use for that. So let's go ahead and look at an example problem. So number 1 says if I have 4 moles of gas, so we know 4 moles, that'll be N, at a pressure of 5.6 atmospheres, P, and a volume of 12 liters, volume, what is the temperature? So temperature is our question mark here. And so we know our formula is PV equals nRT. So let's go ahead and plug in what we know. We know that our pressure is 5.6 atmospheres. We know that our volume is 12 liters. We know the number of moles of gas is 4 moles. And we can pick R. Now we see that pressure is measured in atmospheres. So that means the R value that I want to use is 0.0821 liters times atmospheres divided by moles times Kelvin. Okay, and then we have T for temperature. Now we can leave the T here, or I know many of you would like to substitute the T to be the variable X. That way you know what you're solving for. It can be solved either way. And so what I'm going to do first is I'm going to simplify both sides. So if we simplify the left, we will, by multiplying 5.6 times 12, okay, you're going to get 67.2 atmospheres times liters. and that's going to still be equal to, and I'm going to simplify the right by multiplying 4 times 0.0821, and you get 0.32, let's see, 8, and then moles is going to cancel out with moles, so I have liters times atmospheres divided by Kelvin times x. Okay, and so in order to get x by itself, we're going to divide by 0.328 liters times atmospheres divided by Kelvin on both sides. 0.328 liters times atmospheres divided by Kelvin. And we see that that cancels out on the left side, so we're just going to have x is equal to, atmospheres cancel out, liters cancel out, all you have left is Kelvin, and 67.2 divided by 0.328 is going to give you 204.9 Kelvin. And so that is the temperature. So you literally just plug in what you have and solve. And so for questions number 2 and the rest of them, we're going to let you practice those on your own. And if you're in Miss Allison's class, your teacher has a copy of the key and can check your answers for you. Okay, now, the last thing that I want to talk about is Avogadro's law. Now, as you recall, we know that Avogadro's number is 6.02 times 10 to the 23 particles per mole. Okay, and I'm sure you're wondering, okay, well, if that is his number, then what is his law? And so I want you to think, what happens to a balloon when you blow into it? Well, when you blow into a balloon, the carbon dioxide from your breath, or from your lungs, really, go into the balloon, right? And it inflates. That's what happens. And so what they're saying is that the number of particles is directly proportional to the volume. If you increase the amount of CO2 that's inside the balloon, the volume goes up. And so what Avogadro's law kind of said was that 1 mole of an ideal gas takes up exactly 22.4 liters of space. And so this kind of leads to an updated mole map. Okay, so we know that we have moles in the center, and we've always said that you could change from moles into, hold on, let's get my pen back, moles into grams, and we said that you could change from moles into particles, or formula units, molecules, and atoms, and we've learned that you could change moles into moles of something else, right? You could do that for any of them. Okay, now what you might not be aware, and just as a quick review, we know that this is through molar mass, this is through Avogadro's number, and this is through our mole ratio, or the coefficients in the equation. But what you might not also be aware of is that you can change moles into liters. You can change it into volume. And the way you do that is by saying that 22.4 liters is equal to 1 mole. And so that means we can use a little bit of stoichiometry, a little bit of our t-charts in order to determine exactly what would happen in this case. By using stoichiometry, let's look at this first problem. It says, how many moles of an ideal gas will fit inside a 1,000 liter canister? Okay, well, so we have volume, and so what we want to do is we want to change liters into moles. Okay, so if we have liters, so 1,000, oops, let's fix that. 1,000 liters is our given. And because we start with liters, we put liters on the bottom. And on our mole map, liters is only connected to moles, which is good because that's what we want to change into anyway. And our mole map tells us that 22.4 liters is equal to 1 mole. But we don't have just 22.4 liters, we have 1,000. So what we can see is that our liters are going to cancel out with liters, and in our calculator we would put 1,000 times 1 divided by 22.4, and what that will give us is 44.6 moles. So 44.6 moles of an ideal gas will fit inside a 1,000 liter canister. Okay, so you can see that was just a quick one step. But as you know with the mole map, if you can do one step, you can continue on and change into other values. So let's look at a slightly harder problem. So here it says how many grams of CO2, so they want to know grams or mass, under ideal conditions can fit inside a 2-liter bottle. So here, if we have 2 liters, okay, we eventually want to get to grams, but the only thing liters is connected to on the mole map is moles. So we have to go to moles first. And we know that 22.4 liters is equal to 1 mole. And then once we're at moles, we can change from moles to particles, moles of something else, or grams. And we want to go to grams, so I'm going to put grams on the top. Now, we know that in order to go from moles to grams, we know that we use molar mass. And the definition of molar mass is how many grams are in 1 mole. So we have CO2. So let's figure out the molar mass. We have carbon, which we have 1 carbon and 2 oxygens. We multiply them by their mass on the periodic table. So carbon is 12.01, oxygen is 16. So 1 times 12.01 is 12.01, and 2 times 16 is 32. And when we add them together, we get 44.01 grams per mole. And so we see that that 44.01 should go right here, 44.01. And let's double check our units to make sure they cancel out. So we have liters, cancel out with liters, moles, cancel out with moles. All I have left is grams, which is excellent. And so when we put this in our calculator, remember if the number is on the bottom, you divide by it. If the number is on the top, you multiply. And you always start with your given first. So in your calculator, it should look like 2 divided by 22.4 times 44.01. Now, notice I skipped the ones, and the reason why I did that was because multiplying and dividing by 1 doesn't change your answer at all. And so when we do this and put this in our calculator, we will see that 3.93 grams of carbon dioxide can fit into a 2-liter bottle under ideal conditions. So that's not a whole lot, and that's why most of the time when we're putting things into a bottle, it's not under ideal conditions. We put a lot of pressure on it to force more moles inside the situation or inside the bottle. So let's look at some conceptual questions just as a review, because as a reminder, you have a quiz on Friday, and so we want to make sure that we are feeling well prepared for it. It says, if a balloon's volume is decreased by a factor of 10, what will happen to the pressure if the temperature is kept constant? Well, one thing that we can think here is, let's think back to really any of the demos that we saw with the first one. But if you got to see what happens to a marshmallow when it's inside a syringe, okay, we know, or if you just recall from your gas laws, that pressure and volume are indirectly proportional. So if your volume goes down, your pressure goes up. Okay? especially if temperature is kept constant. And so what happens is if the volume goes down by a factor of 10, that means pressure will increase by a factor of 10. So it means it'll go up 10 times higher than it was. And so number 2 says draw a picture that demonstrates what would occur to the volume of a ball if the temperature increased by double. Okay, so let's look at this. So what would happen to the volume of the ball if the temperature increased by double? Well, so remember our formula for volume and temperature is like this, right? V over T equals K. And so if your volume goes up, your temperature goes up, and vice versa. So here, our temperature is going up by double. That means my volume is going to go up by double. So let's say this is the ball. Okay, it's got a volume, and this is at your initial, right? And then here, if the temperature is doubled, then the volume of my ball is going to go up as well. So 1, 2, it will go up. Now, is my circle exactly double? Probably not, because I'm a terrible artist, but you get the idea. So hopefully this has helped you. You should have plenty of gas law practice problems, and yeah, so good luck on your quiz on Friday, and don't forget that I'll be posting final exam review videos over your study guide on YouTube shortly. So good luck, guys.